All right. Well, first of all, thanks to the organizers for inviting me to talk today. The title of the talk is Holographic Boundary Actions in AdS3 CFT2, Revisited, as you just said, and it's based on a paper from last August. So unfortunately, I won't be able to say everything I would like to say. So you can, I mean, if you're interested in learning more, you can find much more material in that paper. All right, so the starting point of this work is essentially in trying to answer this very basic and general question in AdS-CFT, which is how do we derive the generating functional for stress tensor correlators in AdS-CFT. And in principle, we know how to do this because we have the AdS-CFT dictionary, which was formulated by Gubser, Klebanov, Polyakov, and Witten in '98, is often referred to as the GKPW dictionary. And it essentially tells you that there is an equality between the generating functional or partition function with sources of the CFT with the path integral of the gravitational theory in the bulk of AdS. So on the right-hand side, we have path integral over bulk fields. In particular, there is the bulk metric G mu nu, and there is a collection of other bulk fields. Maybe there are supergravity multiplets. Anyway, there are other bulk fields. And the path integral is weighted by an action which again may be the action of supergravity. And in addition, very importantly, we have to impose boundary conditions on the bulk fields at the conformal boundary of AdS. So in particular, we ask that the boundary value of the bulk metric is the background metric of the boundary CFT, and associated to each additional bulk field, there is a conformal primary operator in the CFT, and we ask that the boundary value of that bulk field be equal to the source, which is arbitrary, associated to that primary operator. And in principle, from that, you can compute all correlation functions. If you have the generating functional, you take derivatives with respect to the sources, and that produces all the correlation functions of the theory. However, note that this equality here is at most formal, since on the right-hand side we have a path integral, which we don't know how to compute. We don't know whether it converges at all. So this is really schematic. There is a regime, however, where we can make sense of this formula, which is the semi-classical regime on the right-hand side. Since in that case, you can essentially evaluate the path integral by saddle point, and maybe you can compute loop corrections to it, and that starts making sense. And this is precisely the regime in which I'm gonna consider. So here I'm going to consider the regime of large central charge in the 2D CFT, which will correspond to the regime of small g Newton in the gravity theory, since we have the Brown-Eno relation between C and the inverse of the Newton constant. So all that we have to do in that regime is to solve the classical field equations in the bulk, satisfying the appropriate boundary conditions that we have imposed. And then we simply have to evaluate the gravitational action for those classical solutions. Here, I'm only going to be interested in correlation functions of the stress tensor, so I can set all other sources j to 0. And in fact, it's enough to consider pure gravity in AdS3. All right. So in principle, it's clear what one has to do. In fact, it was a surprise to me that there was no paper where this computation was described in this way. There are a series of papers that do describe the stress tensor generating functional in AdS3 CFT2, but not relying on this GKPW dictionary. And in fact, the method they used is relatively mysterious to me. There is, however, one paper where this computation essentially has been done. It's in a little-known paper by Steve Corlip in 2005. But the author does not give the interpretation of an AdS-CFT generating functional. It does not mention correlation functions of the stress tensor. And the reason why is because Corlip has in mind a completely different subject in mind, which is the Hamiltonian reduction of AdS3 gravity to a boundary Liouville theory, as was derived some years before by Coussard and Nguyen. And this was very confusing to him because he does this computation, he wants to compare it with the result of Coussard and Nguyen, and he finds that it doesn't agree. There are some differences between the two computations. So here what I want to do is to first review the derivation of the AdS-CFT generating functional, following Corlip, but phrasing it within the context of holography, and then clarify the differences with the Hamiltonian reductions that Corlip had in mind, but could not reproduce. And what I wanted to do is to reflect on recent discussions about ensemble averaging in AdS3 CFT2, but unfortunately, I don't think I will have the time to do that. Okay, so this is the plan for the rest of the talk. First, I will set the expectations by simply discussing the generating functional for stress tensor correlators in any 2D CFT. In fact, this generating functional is universal. It's known as the Polyakov action. And the reason it's universal is because there is, in 2 dimensions, you have the conformal group, which is infinite dimensional and fully constrains the form of the stress tensor correlators up to 1 number, which is the central charge. So then, once we understand this, we can see how to derive this Polyakov action within AdS-CFT. So this I will do in the metric formulation of gravity. I will quickly tell you that it's also possible to do in Chern-Simons formulation of 3D gravity. And then I will contrast those computations with the Hamiltonian reductions of Coussard and Nguyen, and with the most recent one by Kotler and Jensen. And I'll end with a few comments and open problems. All right, so let's start with a pure 2D CFT discussion and the description of the generating functional for stress tensor correlators. So here we have Z of Gij, so this is the partition function of the CFT with arbitrary background metric. And this background metric acts as a source for the stress tensor. So we can define a related quantity, W, And this is sometimes called the effective action. It's also called the generating functional of connected correlation functions. And the goal is to determine what W is. So Polyakov taught us how to do this. We can start from the trace anomaly relation. So we know that the trace of the stress tensor VEV is related to the curvature of the background metric, and the coefficient of proportionality is the central charge. But this quantity here, the stress tensor VEV, is also the derivative of W with respect to the metric. That follows from the very nature of the generating function. And now you can actually integrate this relation, and that's what Polyakov did, in order to find what W is. And what you find is some non-local functional, because it involves a 1 over Laplacian, so the inverse of the Laplacian. There are two occurrences of the Ricci scalar, and we have the central charge up in front. So that's the result. There is an alternative way to write it. So for that we need to introduce some scalar field phi that solves this box phi equal R equation. And then we can actually rewrite the effective action as something very familiar. So this is just the action for a Liouville field, and phi is the Liouville field. So indeed, if you put phi equal box minus 1R back into the action, you recover this first expression. Here it's very interesting to note that under a Weilry scaling of the background metric, phi actually shifts by this quantity omega. So we can say that phi is the pseudo-Goldstone mode of broken Weil invariance. And Weil invariance is broken precisely because of the central charge, or because of the trace anomaly. Something also interesting to note is that if you compute from this effective action the stress tensor VEV by just taking one derivative with respect to the background metric, you find this expression in terms of the Liouville field, and this precisely coincides with the classical stress tensor of this Liouville theory. All right, so that sets the expectations for what we should look for in computing the generating functional within the AdS3 correspondence. So now let's try to do it. Here, so we're looking at three-dimensional gravity with negative cosmological constant. We can pick a gauge known as Pfefferman-Graham gauge, and the only remaining degrees of freedom sit in this component of the metric. So rho is the radial coordinate. It goes to 0 at the conformal boundary. Rho equal infinity is deep in the interior, and the xi coordinates are the coordinates parallel to the boundary. So here it could be the ZZ bar, for example. We're in 2 dimensions. I mean, the boundary is 2 dimensional. Then we can expand this metric component Gij as asymptotically close to the boundary, so in a rho expansion. it happens that in 3 dimensions, this expansion actually truncates. So when you solve Einstein's equations, you don't need to go to higher order. This expansion is actually exact. And there are only three coefficients. The first one is the boundary value. It's interpreted as the background metric for the dual CFT. I also call it G tilde. Then we have G2, which is given here. It's essentially related to this tensor Tij. This tensor is conserved and its trace is proportional to the Ricci scalar of the boundary metric, and this turns out to be the stress tensor of that through the AdS3 dictionary. So G2 is essentially related to this stress tensor of F, and then G4, this is the solution for G4. It's not very important. Okay, so from the discussion in the CFT, it's obvious that the Polyakov action, which is the generating functional for stress tensor correlators, is entirely due to the conformal anomaly, or said differently, the breaking of Weier's scaling invariants. So in order to treat the problem correctly, we need to understand how this Weier's scaling transformation is realized in the bulk of AdS. So that's what we do here. In fact, this has been understood some 20 years ago. There is a class of bulk diffeomorphisms known as Penrose, Brown, and No diffeomorphisms that act as Weier's scaling at the conformal boundary. So this is their action. And these diffeomorphisms, you can understand it as a change of coordinates of this form. And essentially, it's just a rescaling of the radial coordinate. A rescaling that that depends on the location at the boundary. So it's not homogeneous. And this is important because usually what people do when they do holographic renormalization, for example, is that they introduce a cutoff boundary at rho equal epsilon, where epsilon is just a fixed number, a small number that you take to 0 at the end of the computation. But you see that if you do that, you lose Weier's scalings. So what you want to do is to allow Weier's scalings to act within the solution space of your theory. And for that, you need to be a bit more flexible in the location of your cutoff boundary. So instead of saying rho is at epsilon, that the cutoff boundary is at rho equal epsilon, you need to adopt something more general and say that rho is at epsilon, which is a small parameter, but times some free functions of the boundary coordinates. And under Weier's scalings, this quantity omega will shift. So what we can expect from the discussion I had before with the Liouville field is that since this is the quantity that shifts under Weier's scalings in the bulk, we can expect it to end up being the Liouville field for the Polyakov action. And this will be essentially true. All right, so this is just a picture of what we're doing with the cutoff boundary. So rho equals 0 is the conformal boundary at infinity. Usually one would put a cutoff surface at rho equal epsilon, but we want to be a bit more general and allow the cutoff boundary to fluctuate. And this is crucial in obtaining the correct result. So now that we've understood that, we can evaluate the action, the gravitational action on shell, following the GKPW dictionary, and see what we obtain. And what we hope to obtain is the Polyakov action. So the action is, as always, the Einstein-Hilbert action in 3 dimensions. You also need the Gibbons-Hawking boundary term because we're imposing Dirichlet conditions. And when you evaluate this on shell, there are some divergence in epsilon. So as you take the cutoff parameter epsilon to 0, you get a 1 over epsilon divergence. And to cure that, you need some local counter term at the boundary. So you add this, and now you can evaluate the regulated action plus the counter term, take the limit epsilon to 0, and what you find is this expression, which indeed you recognize as the Liouville form of the Polyakov action. So note that there is no boundary condition on this function omega here. So at this point it's still off shell, but once we put it on shell, so we solve box omega equal R, this becomes the Polyakov action. All right, so that's good. We can actually play a similar game in the Chern-Simons formulation of 3D gravity. So let me remind you how to write down 3D gravity in Chern-Simons formulation. So first you need to go to a first order formulation of gravity. So in terms, instead of metric, in terms of some tetrad field, EA, and some spin connection omega A. Then you take the sum and the differences of these quantities to construct 2 gauge connections that are valued in the SO2,1 algebra. And the reason they're valued in the SO2,1 algebra is because we're multiplying them with, so these quantities, we're multiplying them with the generators of the SO2,1 algebra. Once you have done that, once you have an SO2,1 valued gauge connection, you can write down Chern-Simons theory. This is it. And what can be shown quite easily is that the Einstein-Hilbert action is just the differences of 2 such actions. So it's the difference between this, well, it's the difference between the Chern-Simons based on this connection and the one based on this one. And the equality is valid up to some boundary term. Okay, so then we have to take care of the appropriate boundary conditions and appropriate boundary terms. So I'm not going to go too much into the details of that, but what you want to do is, as in the metric formulation, you want to fix the background geometry at the boundary. So in metric formulation, you want to fix the background metric. In first order formulation, you want to fix the background tetrad and background spin connection at the boundary. And this is achieved through these boundary conditions. And in order to have a well-posed action principle, you need those boundary terms. Now, again, I'm
sorry, 5 minutes left for your talk.
All right. Thank you. So now I'm skipping the computational details, but again, you can evaluate the action on shell using the same counter term as before, and you find again something that is a Liouville action. There are different coefficients, but when you again evaluate, when you put omega on shell, this becomes the Polyakov action with the right coefficient in front. So this appears a bit non-trivial because the Liouville form of the action is different in this case or in the metric formulation, but once you solve for the Liouville field, both computations agree. All right. So this, this is essentially what Karlip did. I mean, I phrased it in the context of the AdS3 correspondence, but he was unhappy because he could not recover the results of Coussard and Nguyen, who did something different. But at the end of their computation, they also get something that one would call a Liouville theory, although it is slightly different. So okay, what do? They start with restricted ansatz for the metric of 3D gravity. In particular, here you see that at leading order is just dz bar. So that means that the boundary metric is flat. So the sources for the stress tensor are turned off. And the only free functions here are and L bar to be anti-holomorphic. So the ansatz is different. There are no boundary sources turned on, but the metric is still off shell. All right, so then you can simply evaluate. So in Chern-Simons formulation of 3D gravity, you can evaluate the action on those restricted ansatz, and after field redefinition, what you find is this expression. So it's a boundary action. T and phi are the coordinates on the cylinder at infinity. And here we have this this action, which is a Liouville CFT with a non-zero cosmological constant. So there is this potential term, and it's usually interpreted as non-zero cosmological constant. And here is where Karlip was confused, is because he found a different Liouville action with arbitrary background metric. Here we have flat background metric, but we have also this potential term. But the reason is that they're completely different. In fact, if we were to evaluate this action fully on shell, so imposing Einstein's equations with the ansatz that Coussard and Nguyen used, we would find 0. While with arbitrary sources turned on, we find the Polyakov action. So these are just different objects. There is a more recent Hamiltonian reduction due to Kotler and Jensen. It differs from the one by Coussard and Nguyen by a different parameterization of the fields, and they find this answer. Again, very similarly, this action corresponds to all sources being turned off. And if you were to impose all the bulk equations of motion, in particular d bar phi equals 0, here the action would vanish. This formulation has a nice group geometric interpretation in that it's the geometric action on the first exceptional coadjoint orbit of the Virasoro group. So that's interesting. But again, it's different from the AdS CFT generating function. All right. That's essentially, yeah, my time is essentially up. So I can give a few comments. So there are two types of boundary actions that you can look at in AdS. There are the generating functionals that allow to compute CFT correlation functions. For that, you need to turn sources on at the boundary. And there is a second type of boundary action where you turn all sources off and you keep some modes off shelf in the bulk. And these are so-called Hamiltonian reductions. It's very interesting because although these are two different types of objects in AdS3, they share a lot of similarities. In fact, there is a way to write them all as geometric action on coadjoint orbits of the Virasoro group, which adds to the confusion. And related to that, so yeah, I have a, no, I don't have the slide. Related to that, in 2D CFT, those geometric actions can play two roles. One is that of a generating functional, the other is that of the effective action for stress tensor exchanges and computation of Virasoro identity blocks. Okay, that's all I wanted to say.
Okay, Kevin, thanks. Thanks for your interesting talk.